Welcome back to the second keynote. Before I introduce the speaker, let me switch quickly to a short message from our generous sponsor, which is MathWorks. Great. Thank you very much, MathWorks, for sponsoring generously L4DC. And we're back to where we were. My name is Alessandro Abate. I'm one of the chairs here, and I work in the computer science department. It's my personal pleasure to welcome Shankar Sastry to deliver the next keynote at L4DC. Shankar is one of the most prominent scholars from the University of California at Berkeley. To do good justice to his achievements and to CV would take most of the next hour. And since almost everyone in the audience will be familiar with his work, will have, for example, read one of his many books, ranging over adaptive control, over controlling robotics, nonlinear control systems, computer vision, machine learning, and I could continue. Since most of us are familiar with the work of Shankar, let me perhaps address the few in the audience that aren't yet familiar with him by perhaps just congratulating them on their wisdom or perhaps on their good fortune to show up here today to witness the much anticipated keynote, which is titled Learning-Enabled Multi-Agent Systems in Societal Systems Transformation. Ladies and gentlemen, please join me in welcoming Shankar Sastry.
That's a very kind introduction, and it's really a pleasure to be here. There used to be a time when there used to be a Berkeley-Oxford summer program, and by coincidence, it used to be always the week after Wimbledon. And so it's perfectly timed that L4DC is also very much the week after Wimbledon. Okay, so I want to talk to you about what we've been dubbing as learning-enabled multi-agent systems. And, it's got a history, and I want to say something because it also relates to several people in the audience, like Alessandro talked about. In 1978, the automatic control transactions had a special issue on multi-agent systems. And, it was, I was just starting off in grad school, and there were some wonderful, wonderful topics. And at the time, I was really struck by the use of game theory. And really, there were some wonderful, wonderful papers in this special issue. April of 1978 is the specific issue of the automatic control transactions. And, there were some really far-sighted people. Time Air's advisor, Larry Ho, was one of those key exponents. Time Air himself has been really somebody who has sort of plugged the notion of really thinking about multiplayer games. And, he was telling me also, there were many years where almost like he was a lone wolf, but now you see it's certainly going to be central to what I'm going to talk about. Also my colleague Praveen Varaya, and I think it is really a resurgence, of course, where the technologies have changed. And I want to talk a little bit to demystify the topic which is sort of used in boardrooms, called digital transformation. And this term digital transformation is used to mean really about how do you structure awesome new services around the fusion of IoT, machine learning, and the cloud. It began with cloud computing, of course. Now there's computing on the edge. And of course, the part that I want to spend a lot of my time talking about is really what difference it makes when you introduce these technologies into societal systems. And there are two themes that I'll highlight, and I'll do that in a second. But just to plug whose work this is, I'm really the mouthpiece for almost complete PhD dissertation of Chinmay with contributions of Manchi Wu. She's at Cornell, actually. She's contemplating a move. Kshitij, who's finishing his PhD. Lillian Ratliff at the University of Washington. Eric Majumdar, who's at Caltech. Okay, so let me dive right in. So it is true that AI, ML powered automation services are really transforming a lot of our societal infrastructure. I think transportation and energy were the start, but financial services, water, power, telecom, they're all being transformed. And the issue, of course, is and they're all geared around having data and trying to understand what people want to do. And why do you need to understand what people want to do? Because, people don't sit and let algorithms be done to them. When people put up an algorithm, people will modify their behavior. And so you've got to design these systems on the assumption that people will modify their behavior. And the question is, in my opinion, a lot of the standard machine learning framework doesn't actually address this. And so what I want to do is, really it's a shared heritage, actually of AI, control, also machine learning, to really think about what do you do when this happens. So what are the two challenges? Oh, and this is sort of the algorithms interacting with machines. That's what learning-enabled multi-agent systems are. And why are there limitations? The first one is you're interacting with multiple different kinds of agents. They are seldom homogeneous. Occasionally you'll talk about populations of agents, and there's a little bit of that, but then generally they're not. They're not always myopic. They don't make decisions just to optimize the next step. People learn to play soccer and score one goal in 90 minutes or something like that. That's couldn't work for me. And their self-interest is not aligned with that of others, and also quite often with societal goals. And because of privacy and scalability considerations, you're seldom able to share all of this information between agents. And so the challenge is that as a result, there's non-stationarity in the feedback received by any one of them, and you need to have algorithms which deal with that. The second challenge is that when algorithms interact with machines, you need to overcome these biases and correlations. You make assumptions. decisions are uncorrelated. And they're not. They really are. They're correlated by decisions you take. And you've got to make efficient and fair decisions. And this efficiency and fairness has to do with the fact that, you introduce these awesome new services for transportation, Ubers and DoorDashes and all kinds of things. But you've got to worry about whether they apply equally to all elements of society. I'll try to give you an example of how, if you don't, bad things can happen. And how do you sort of build an algorithm that takes this into account and talks about both societal efficiency. Also, the other thing about efficiency is, if you believe, there's good behavioral data to say humans are not utility maximizers, even though this is sort of the dominant paradigm of AI. I won't dive into that as much here, but even so, even if people were trying to maximize their own utility, there's a gap between the individual utilities, the individual Nash equilibria, and the societal good. And that's, some people call it price of anarchy, or misalignment, I think, is price of anarchy sounds too dramatic. It's really a lack of alignment between what society needs and what society wants and what individuals want to do. And so the question is, how do you incentivize groups of agents to do the right thing for society while being selfish? And that's what I want to talk to do. And of course, if you don't do it, bad things can happen. We all have this experience of how having all kinds of map algorithms are converting, really leafy, quiet side streets into busy thoroughfares because some algorithms decided it's a more optimal trajectory to take you through, or as it happened to so many of you, I'm sure you've landed up in little alleyways that you wonder why you're. It actually happened to me a couple of weeks ago in Italy, and I got stuck in an alleyway which was too small for my car, so I actually had to back out of it. Other things, coalitions. These people. There was some of these lawsuits about how do drivers manipulate pricing systems. How do you have? So let me not go through each one of these. In Berkeley, in Oakland, Oakland's a city adjoining Berkeley. There was something called predictive policing. Predictive policing was an AI algorithm which was aimed to determine where there was more crime and to put more police stations where there was more crime. And that was billed as the use of AI to take the city, which was under some federal scrutiny for bad policing. What's the problem with putting more police stations where there's more crime? It reinforces bias, right? Of course you're going to find more crime where you put more police stations. And so when you design these algorithms, when you design even simpler versions of this, where you do tolls, you got to pay attention. You got to pay attention to, and you got to write a formulation for these. So I'm going to try to tell you what the mathematics of this is, and we think it's a wonderful new subject which really goes into all of these. And most importantly, I think it's critical to give policymakers options. There's too much talk about regulating AI. I think it's true that you've got to have guardrails, et cetera, but it's got to be in terms of a set of options to policymakers. And policymakers, it can't be that somebody sort of says, here's what policy ought to be, and you conform. And so you've got to be able to provide people with options, and I'll show you how you can do that. Okay, so two challenges, and the style of this talk, and please cut me off. There you are, Alessandro. I think I'll finish in time, but two challenges. The first is to incorporate this non-stationary feedback to designing decentralized algorithms, and the second one is about what's called incentive design or mechanism design for aligning user preferences for efficient, fair, and safe operations and learning. AI, machine learning, everything you've been seeing is really at the heart of all of this, and the algorithms are all built in, so have no fears. Okay, so two sets of vignettes. One is addressing challenge 1, which will be about incorporating non-stationary feedback to design decentralized learning algorithms, and the other one is the incentive design, and there are these two examples on the left and 3 examples on the right. And I know it's a lot to cover, and you have a sinking feeling when people put up so many different slides to cover. I promise I'll keep the technical details low here. There's a very interesting technical detail and there's very interesting algorithms, but let me sort of. Okay, so let's get started with decentralized learning and matching markets. We all know this, there's TaskRabbit, Airbnb, DoorDash. The agents and firms, the agents have their preferences, firms have their preferences, and you're going to try to line them up. Okay, so here's how it works. There are 3 agents, the 3 firms, 3 people offering jobs on TaskRabbit and 3 people who want jobs done. Those are the firms. And, you have, let's say, firm 1 prefers A1 to A2 to A3, and so on and so forth. If A2 and A3 both bid on firm 3, there's a collision. Firm 3 decides that A2 is better than A1, it prefers it, and then it puts it in together. And of course, this is beginning to look a lot like bandits. So the successful match results in noisy utility functions, UAFF. And collision results in no utility. Okay, and now we want to do this with unknown agents. Let's first talk about a wonderful algorithm called the Gale-Shapley algorithm, or the deferred acceptance algorithm, for what happens when agents know their preferences. When the agents know their preferences, this Gale-Shapley algorithm, I made a little leisurely, but let me just lead you through it. It says each agent requests to be matched. If there's a collision, then of course, you provisionally tell that person, go away, try again. The other person tries again. There's a collision, that goes away. And you put it together. And that algorithm, wonderful, wonderful decentralized algorithm based on local information, converges to a stable match. So again, the details of what you mean by a stable match, a little bit like a Nash equilibrium, except it's put in this context. And this algorithm is just spectacular, finitely many steps. And the question is, what do you do if the agents do not know their preferences? And so there's a lot of work. My colleague Mike Jordan got me interested in this by thinking about a version of this in the bottom right-hand corner, so we thought we'd better go all the way to the upper right-hand corner. So let me give you an idea of how we try to think about this. So it is, each person gets an unknown utility. It's got a probabilistic utility function. F sub A is the choice of firm A, F by actor A, and then it's a stochastic utility function. If there is a collision, you get this Y of t is 0, and if it's successful, it's 1. And so the question is, how do you redesign these algorithms? And our short answer to this was to use 2 kinds of bandits. One is a stochastic bandit module for choosing which firm to query. And furthermore, based on the observing the kinds of collisions that you have, you choose the probability of pulling the appropriate arm, and you use a different module called an adversarial bandit module in order to be able to influence that. And so this is the pictorial version of this, the stochastic bandit algorithm, the many standard versions. But then what's new is that you choose even adversarial bandit algorithms, there are several standard ones, X3, and there's a modification of X3, which has mirror descent built into it. But then if you add into it a little bit more, which I am not telling you all the details of, about how you do the pruning on top of that X3. But when you put it all together, then you put together the stochastic bandit module with the adversarial bandit module to be able to learn. So that's where the learning comes in, to be able to learn the preferences and deal with what other people are doing. And you do this partly by seeing what people's actions are, what the probability of collisions is, and of course you have to build in a little bit of exploration so that you also put it in. And using all of this, you can come up with a regret bound, which grows like a log t, and there's another little term called path minus length, which I don't want to dwell on, which is really about making sure it's not excessively pessimistic. If you just stick stick these two bandits together. It's too pessimistic an algorithm. And if you put this all together, there is a slight generalization of this stable match due to some markets called alpha reducible. If every sub-market has at least one fixed pair is like a Nash equilibrium, then you can show that the regret bound, if you put the 1 over t, it's log t over t. But if you don't have the 1 over t is not subsumed in the left-hand side. It's not the average regret. It's the total regret. And that's proportional to log t divided by a measure of the deviation from your choice with what happened at that exact time step. That's the number delta. And that's log t. So, I think that just to give you an example of how it is that you can actually discover preferences during the course of operation. And during the course of operation, by doing a little hack, which I didn't tell you about the exploitation part of the hack beyond X3, that will give you regret bounds over log t. And that, I think, is, all regret bounds should be taken with a grain of salt. So, the problem with regret bounds is that regret bounds are aggregate quantities. You lead your life one sample function at a time, not ensemble at a time. And that's why I was complaining to Lee now about the safety versus safety, I think, is a sample function property, whereas all these are aggregate properties. But anyhow, so the message behind this is about how you try to not be excessively pessimistic in how you choose the matching to do this. Okay, now a variation of this philosophy for doing about multi-agent reinforcement learning, I think we thank Lee for having put up the framework, so I'll skip through this. The difference, I'm going to try to do it all decentralized, meaning that there are multiple agents, they're interacting with each other, and they're not allowed to know about each other. And there's both competitive and collaborative interaction. A little bit about the literature that's in there. And the key feature that we discovered is that people say that reinforcement learning comes to age every 10 years. The new resurgence, and multi-agent RL is no exception to this. Every 10 years it jumps back into prominence. But we found out that apart from the heuristics, one of the few places that you can prove algorithms, prove convergence results in multi-agent RL is when the underlying games are potential games. And so the question is, can you manage to relax this? And of course, the other problem is it's hard to find potential games around. Some routing games are potential games, but otherwise. So what we did was to come up with, and I think for different reasons, it's not called an epsilon potential game, but an alpha potential game. If, and again, the details of this are probably not critical. It just says it fails by a quantity which is alpha times the norm of the distance between the policies. There's a function phi, which would have been the potential function for the game, for the game, up to a factor alpha times the norm of this. And that's called an alpha potential game. And amazingly, with these alpha potential, of course, all potential games are alpha potential games, etc. But if you put this together for alpha potential games, and I want to bring you to this notion of in learning, and I think this goes back to our heritage of adaptive control. Control laws need to be fast. You respond quickly to changes in state. But, to slower changes, policy, the nature of policies, needs to change more slowly. And so if you have the sort of timescale separation between how quickly you adapt your policies and how quickly you do your feedback, the next step, and how slowly you adapt the policy, then you can come up with convergence results. And so now I'm going to, the next 2 slides, I'm going to give you sort of a smattering of these results. So here's an example of the value function update would be the instantaneous one that you go quickly. This is specific temporal difference learning-based update as a specific example. The policy update, on the other hand, is, you take a look at everybody, and then it's like when you play a game with somebody, or you play chess, you play soccer, you try to determine the strategy, and then you adapt your strategy. You don't have time to compute Nash equilibrium, so best response, BR is the best response for your best estimate of the person's strategy to that, but you do this more slowly. And that's the second piece of this, the policy update. And you could think of it as an actor-critic kind of algorithm, but the difference is not just another heuristic. Again, there's some assumptions, somewhat modest assumptions. The biggest assumption, of course, is the two step sizes, alpha n for the TD update and beta n for the policy update. They both, their sums go to infinity, but then the timescale separation is written out as lim sup is good enough. Lim sup of beta n over alpha n goes to 0. There's one other thing for if the rates of asynchronicity of the different agents is different. There's a way to put a bound on it. So let me not get into that last step. And the informal theorem is that these kinds of algorithms with slow policy update and quick updates of learning in the based on the Q learning, etc., results in a convergence to an approximate Nash equilibrium. And the approximation of Nash equilibrium is given by some function g, which in fact goes to 0 as alpha goes to 0. There's some interesting bounds on this g of alpha, but in the interest of not dragging you too much into the details, so this philosophy that emerges is really that of some things you have to respond fast, other things you have to respond slowly. And perhaps not accidentally, it brings to mind a wonderful little coffee table book, which some of you probably read, called Thinking Fast and Thinking Slow by Kahneman and Tversky. This is a version of thinking fast and thinking slow applied to these kinds of multi-agent RL games. And you massively expand the number of games that you could apply it to. And so it's a whole other interesting story about the applications of this to alpha games. And, for different reasons, we are presenting this to the operations research community. I have a colleague called Shingo. She's in operations research, so she has dragged us into that. Okay, so that's an example. There's more to say about all of these, but I just want to give you a vignette and want to be sure that we don't keep you from lunch. So let me tell you a little bit about incentive design. Okay, in incentive design, this is really aimed at combating the gap between Nash equilibria and societal good equilibrium. And I want to give you a sense of how you try, and if you leave things the way they are, there is a gap between the two. The question is, can you add an incentive scheme, thereby modify people's individual utility functions so as to get the Nash equilibrium to be closer to the societal good equilibrium? So I want to give you an idea of what the theory looks like, and then I want to show you, I talked about talking to policymakers. So I want to show you what it means to apply it to an example which is about tolling. And so let me, and it's very much in the debate here. Okay, and you've got to learn all this. The designer has only, the societal designer cannot have too much detailed information about the utility functions of the individuals. You can only have small amounts. So it's, and again there you'll see this two-time step story. The incentive design changes more slowly. Everything's dynamic. Okay, so the one thing that we really bring to all of these games is the dynamics. And it's not a one-shot. Things are changing, learning is helping you understand the parameters, and so on and so forth. And so that actually adds a significant amount of complexity. So let me get you through, let me try to work through some of this in a slightly abstract framework, and then I'll apply it to the tolling situation. So, the individual cost of an agent is Li of X, and then let's say that the incentive design is to put a price Pi on top of this Xi, and so it modifies the utility function to Ci of X of P, which is a function of X plus Pi. So think of it as tolls, think of it as taxes, whatever way that you have of being able to modify the behavior. And then, of course, human beings are, once you change the utility function, once you set tolls on roads, they're going to change their behavior, they're going to change their XK, their strategy set, and they might do this either by trying to, if they could compute an equilibrium response, then they'd use the equilibrium response, they'd do a best response, or they'd do a gradient play, which is really to try to minimize along the gradient. The incentive design, on the other hand, so gamma k here is the update rate of the actions of the agent. The incentive designer changes the prices, pk plus 1, so as to minimize the social cost function. In some cases, the social cost function may well be the sum of the utility functions of all the players, but it could be more sophisticated than that. In the case of tolling, it could include total congestion, but it could also include the willingness of people to pay, and really thinking about different segments of the population. And I'll show that to you. And in this particular algorithm, what you try to do in the prices, as in a lot of the econ literature, the prices are adjusted based on trying to find a gradient in the externality induced by people using this. So the way that means is that you take the gradient of Li, think of X as the level of congestion, the gradient of Li tells you how much more congestion is brought on by X using more, by using greater CPU cycles, think of X as the number of CPU cycles that you use, and this phi has to do with melting the polar ice cap, something like that, and so, that's what you put in there. And so, you try to design an algorithm without knowing too many details of Li, and perhaps just bounds on the gradient of their utility functions. And again, the slow incentive update rate is that limit, is as beta k over gamma k goes to 0. Lim sup is good enough, lim is certainly good enough. Okay, and so the question is, how do you analyze these? Everything that will happen is going to be a stochastic version of this, but let's just take a look at the deterministic version of this. In the deterministic version of this story, there are so-called ODE methods, which will come up with ordinary differential equations. You can see that the differential equation on top of the x dot equals pxt, and the differential equation below will depend on, if it's slower, then it'll have a slower time scale. The p will be roughly constant or slowly varying, and it'll have a different differential equation. And the theorem is that under really pretty, the conditions of strong convexity of the individual and social cost functions, the set of fixed points is unique, and the Nash equilibrium induced at the fixed point is socially optimal. Socially optimal in the sense of optimizing phi of x. So not only do the slow updates, the fast updates of individuals' decisions do the right thing, but also over time, the prices converge to the, and this is non-atomic, and could be also generalized to, this is atomic, and it could also be generalized to non-atomic games. And, amazingly, again, in the stochastic control literature, a lot of wonderful, I think Borkar is the fellow that wrote a wonderful set of books on ODE methods, even 2-time scale ODE methods. You didn't have t going to infinity when you talk about stability, you had finite time. So, but it's not insuperable to extend these theorems. And so the theorem is that there is a generalization of this Freudenberg and Levine, and a lot of those names are from the econ literature. If you have this timescale separation and some square summability of gamma k, but it's not L1, but it's L2, and similarly beta k, and the limits go to 0, then you can show that it converges to the fixed point. And in addition, the kinds of theorems that go into the ODE limits are quite interesting in their own right. There was a colleague of mine at Berkeley in math called Morris Hirsch, who had proved these theorems on competitive collaborative equilibria. And roughly speaking, if the Jacobian of the vector field has the same sign, it's the first condition up there, dpi by dx, all the ij entries of the Jacobian are positive. That's one sufficient condition. There are other conditions to make sure that the dynamics stays in the first octant, et cetera. The different methodology that, if there was this one is non-Lyapunov. It's this in mathematics and dynamical systems. There's a rich history of, and so someone was talking about computing invariant sets and all of that, right? So Amy, I think, and so the way the proof goes is really compute appropriate invariant sets. If you could get a Lyapunov function, that would also be useful. And so one example is about how you might apply it to transportation networks. This is an exceedingly hot topic. We are all sitting here in Great Britain, which is an enlightened country, which has real-time pricing of tolls in London. And Singapore is the only other place, only other big metropolitan city. And 3 weeks ago, the governor of the city of New York, of the state of New York, vetoed real-time tolling for the city of New York because she had social concerns. But I'm going to tell you about her social concerns, and there are real social concerns. But modulo that, so how does it go? I think the first order congestion is caused by each one of us trying to minimize our transit time without caring for the utility of society. And tolls are supposed to be the way that you even this out. And so that's so travel time, you have a route, an origin-destination pair in this graph theory business, and there's a route associated with this. The toll in each edge, the sum of those tolls is the cost function of an agent. And then, of course, that's the travel time. And then you tack on a toll on top of it. The tolls could be by segment, the way it is in London and Singapore, or it could be in bridges and so on, as it is in several other cities. And you try to optimize the overall congestion. And you can actually show that all of these assumptions work on these transportation networks. And if you had a way of updating the tolls at a slow speed according to not just the exact gradient of each one of the travelers' fees, but just an estimate of this, you can show that a tolling mechanism will converge to the societal optimum. Okay. And this actually, let me not get too sidetracked, but applies to energy markets, it applies to ride hailing, Cournot competition, et cetera. So let me skip this. But let me now talk about what happens. Why did the governor of New York veto what seems like an unalloyed good? And the reason, so let me just lead you through this in the form of a case study. So what we wanted to do was to try to understand, so the tolls this is a picture of the Bay Area, and the only tolls there are these $7 bridge tolls. And somebody wanted to increase some of the bridge tolls to be $10. And there was tremendous, the elected officials like the governor of New York and the Bay Area jumped in and said, hell no. And the reasons for doing this is, as is well understood, tolling, real-time tolling, is potentially is regressive in the following sense. It's too strong to call it regressive, but it favors richer parts of the society over poorer parts of the society. And for example, if you're a wealthy person, you can adjust your travel patterns, so take advantage of the tolls being lower outside rush hours. But if you have to show up at work at a certain time, you're less able to do so. That's the sense in which you're unable to take this into account. And that's the reason that the governor says it's too regressive. The party line is that, if the excess profits are generated, the governments would take the excess profits and use it to provide more public transportation, but you know how taxes go. They disappear into a black hole and they don't necessarily go where they're supposed to go. So we wanted to try to understand what you could tell these people. And, you would not be surprised since 1912, everybody and their uncle has thought about the sensitivity and congestion pricing and all of this. So let me lead you through, now I'm going to apply what you just saw, this 2 time-scale pricing, to this framework. Except I'm going to tell you a little bit about the details. Again, there are origin-destination pairs. People choose a set of routes to go between them. And then we're going to consider many cases tolling individual links, not tolling them in a few places like the bridges, et cetera, et cetera. And in addition, you're going to, also longer routes. The cost of fuel, even in America, has gone up. So, it's you got to take into account the cost of the fuel. And then, in addition, you've got to be able to take a cost associated with the time of travel. And that, how do you convert time of travels into dollars and cents? It's done through a metric called willingness to pay. And willingness to pay is a function of your income level. It's really an understanding of how much you're willing to pay for a minute saved or an hour saved, and how do you take that into account. And the different income types that are doing that, and that's also built in. The different kinds of travelers, and theta super I is the kinds of travelers, the toll cost is the gas cost, and the travel cost of the route. The societal equilibrium is to minimize congestion, but we'll also try to take into account what you can do for, in this particular case, different types of travelers in terms of the willingness to pay. The current situation with the tolls is that it's neither efficient nor equitable. It really, the disproportionate burden does, unfortunately, fall on top of the poorest segments of the society, and it doesn't improve congestion. But if you put all this up with these cost functions, the only big nonlinearity in these cost functions is attributed to a Cambridge professor called Sir James Lighthill. So you guys in Oxford would probably be glad to blame those Cambridge for, which says that the transit time grows as a 4th power, a constant plus a 4th power of the amount of traffic. That's how congestion grows. James Lighthill also did aero stuff and fluid mechanics. He loved these power laws. Anyhow. Okay, so again, I don't want to drag you through the linear, it's all very exciting to do these linear programs, and they're duals, and you take into account the societal good metric. You have a metric which measures how much, you have this parameter lambda, you have parameter y, and lambda is the weighting that it's given, which measures, how much people are paying as a function of what they're willing to pay. And so if you include that in the average travel cost, then you can solve these. It's a 2-step process. It's a multi-step process, actually. It's a game. It's a multi-person game. And, these are quite large. I'm going to show you how it all applies. And I'm going to show you what the results look like of the preceding theory, which is applied to 2 kinds of tolling. Homogeneous tolling, which is every single edge is tolled. Homogeneous and heterogeneous means the following. So homogeneous means everybody gets tolled at the same rate. Heterogeneous means that, it's, in the United States, it's explosive to say it. Different people pay a different toll, but, the way that's implemented is there are grants given to people who are commuting, and another one is so-called fast-track lanes. So you have some lanes which can go faster if you pay more. And that's actually the most socially acceptable way of enforcing this heterogeneity, and it's beginning to be applied, and certainly applied in London and Singapore. You can pay a little extra for certain lanes which grow faster. So that's heterogeneous. And the tolling can be either on all edges or a subset of the edges. And okay, so now I'm going to lead you through what the conclusions are, because we did this to make ourselves popular with the Department of Transportation in Sacramento. So I just want to say that we did this to not, it was really sort of political ground. And here is, so to first order, let me just, so the story is that in the San Francisco Bay Area, by and large, the less wealthy populations are on the east side, which is the side which goes from Berkeley, Oakland, San Leandro, Hayward, etc. The jobs are by and large in the south, and the wealthy populations are in the south. So with the current tolling scheme, it creates a huge amount of congestion on that eastern side, and very little congestion on the other side. And so that comes up right away. We had these three populations. And so, this was not just an academic exercise. So we collected the data. There's things called loop detectors, which detect the traffic on the roads. And then there's a thing called SafeGraph, which is a startup which collects all the cell phone beeps, keeping track of people's locations. It's actually all over the US, and so it's sanitized, so we can actually you get a sense of how people are traveling. And then this willingness to pay parameter comes from census surveys, where and these are examples of the numbers that we got, and they're quite contested numbers. You could say once you start doing this, it's quite contested. And there are many, many interesting ones, but here's a one-slide version of, how am I on time? 5 minutes, okay. So the one-slide summary is that it is actually possible. So here are three pictures. One is the current tolling situation, which is the average transit time is 57. Average transit times are not good measures because some of the peak numbers are a lot harder. The averages mask that. But if you did no tolling whatsoever, the congestion doesn't become a lot worse. In fact, it becomes slightly better. And then if you do this homogeneous tolling, then the average transit time increases. But even if you do the heterogeneous tolling, then it is not significantly changed. And amazingly, you can compute these optimal, the guy called John Kleinberg at Cornell, who helps compute these numbers for graphs and so on and so forth. So there's 1.06. 1.06 doesn't seem like a lot, but with these traffic patterns, there's relatively few bridges and so on. And this is also a story for Manhattan. There are just a few bridges, a few tunnels and bridges and so on that get in there. So, the averages don't decrease by more than a few minutes, about 5 or 6 minutes. But in addition, if you did the homogeneous tolling, a disproportionate burden falls on the poorer sections of the population. On the other hand, if you do this heterogeneous tolling, which is implemented either by these fast track lanes, then you can reduce that quite a bit more. It goes up by a little bit, but you can control this, and there are other mechanisms to address this. And so, and then, the public planners will say, hey, we are reliant, in the Bay Area, the amount of toll that's collected by the authority is about 630 million, 635 million. So we did the calculations with all of these, with the real-time tolling, and it's roughly the same numbers. So it's not like they're making less, but there'd be greater scrutiny on what they did with that 635 million, I guess. Okay, so I think that this is the kind of analysis that was unfortunately not done for the state of New York, but for the governor, Kathy Hochul, really actually, she didn't want the heat, because they were going to do homogeneous tolling. And at $23, anybody who's gone to Manhattan recently, you'll know that the 23 was going to go up to 35 or something. Okay, the last part also I want to tell you is 3 minutes? Okay, I'm going to just tell you 3 minutes part of this. And the people talking about UAVs, I think that air taxis, UAVs, Amazons are all growing. And I have to tell you, the biggest use of UAVs, is actually in the developing world. You know, the country that uses the largest number of UAVs is Rwanda. There are 1 million flights of drones delivering medical supplies in Rwanda. And in fact, it's gotten to be enough flights in Rwanda. Ghana is number 2. I think that Indonesia, Brazil are close behind. Okay, of course, we would love to have air taxis. And so the question is, how do you design a structure, an air traffic structure, especially over urban environments, to be able to put all this together? And again, there, you know, this also holds for regular crude traffic management. For unmanned air traffic management, an auction system is probably the best way to do it. So some of you have experience of Google auctions and second prize auctions. And the problem with second prize auctions is that, does everybody know what a second prize auction is? Second prize auction means that people submit sealed bids for a common good, and the person with the best bid wins, but pays the second price. Pays the price of the second highest bidder. And that's a second prize auction. It's supposed to be a way that you can use. It more accurately reveals people's preferences than the straight auction. The problem is that, since everything is sealed, the bidder, the person running the auction, can make a disproportionate profit, and the Federal Trade Commission is taking actions on this. You may have seen that Google has stopped using second prize auctions in its ad sales now. So we need to do something which has this, a way of auctioning this to deal with these air traffic flights. And again, I want to just sort of say, okay, so it's a long story. You've got to do auctions, but then a version of the auctions that deals with this problem about second prize auctions. And there's a wonderful gang of 2 economists, one at Harvard and one at Stanford, that have proved a so-called trilemma, which is 3 things can't be done together. I don't want to drag you into that. But I think to address that, there's another older concept called Fisher markets, but Fisher markets don't deal with divisibility of goods. Meaning you want to send 0.7 of a UAV in this direction, 0.3 in a different direction. And so you've got to fix all of this. And I think that this is a market-based mechanism for doing unmanned air traffic management. Initially, I think the big users of this will be in places like Rwanda and Ghana, where there's real traffic congestion over Kigali, caused by the number of flights carrying medical supplies. There's no roads. People are using, people would rather have drones deliver emergency medical supplies. Okay, and and the math that goes into this also really an interesting story. Let me just conclude by last week's headlines. As you may know, that in the Paris Olympics, people were going to fly air taxis between Le Bourget and Versailles and all these places, and this was proposed by the Macron government, but the Paris city government duly torpedoed it. And the reasons they torpedoed it is because they claimed that the societal good function did not take into account adequate pollution. They're all electric, so it's not that they're spewing fumes, but there is noise. These rotorcraft actually make noise if they're electrical, and so it's legitimate. But if they had built that in, I think we might have seen them, as you have probably all heard, no air taxis at the Paris Olympics. But I think as time goes on, I think the scheme will be doing it. And I was going to play a little bit of a movie about, at the University of Delft, they have a wonderful package called Blue Sky, which enables you to do these experiments with the Bay Area. So, okay, so let me stop because I don't want to overstay my welcome. So I think this is a fantastic field. It combines learning and control in the most integral way that I can think of, because it's really about learning people. And the problems you're addressing, there are big questions of society. There are questions which I think for-profit companies would be hard-pressed to address, because they're there to, their utility functions are not the societal utility functions, and I'm glad they're not, because they need their stock prices to do well and for us all to invest our retirement appropriately. But I think that the theory that underlies this has to take into account behavioral changes. And certainly, you know, I began by saying utility functions behaviorally, you got to address that too. And it's not just replacing utility functions by prospect functions like Kahneman and Tversky. But, you know, I think we better pay attention to not just turning the crank on utility function maximization as time goes on. And the societal good piece is one piece of softening that story. Okay, thank you very much, and I can take questions.
There might be time for a quick question before we go out for lunch, please.
All right, great talk. You mentioned James Lighthill. I'm sure many of the audience here know that he also wrote the so-called Lighthill Report in 1973,
I knew
which
you
was
were going to bring
responsible
this up.
for the AI winter in the UK.
Can I repeat the story to everybody here? Okay, this is James Lighthill, one of the greatest polymaths of the time. And for different reasons, in 1973, as you correctly pointed out, he was sent to Edinburgh. And Edinburgh, as you know, was one of the places that AI was booming in the United Kingdom. And he wrote this report about how he felt AI, robotics, machine learning was was really not worth supporting. And that had, I think, pretty disastrous consequences for AI research in the United States. I think it really took to Tony Blair to reverse the Lighthill report. I'm glad you remember
So I
that.
was wondering how you would connect this, because another English or Scottish control engineer, Alistair McFarlane, on the other hand, was advocating the use of AI in learning and ideas like Kolmogorov complexity and related things in the context of adaptive control systems.
Hey, okay, I'm just going to promise, this is a little bit of an Oxford plug here. So Oxford, as you know, has had an institute run by a philosopher, Bosworth, who was, and where this has been debated about AI. A colleague of mine, an alum of Oxford, Stuart Russell, is quite engaged in the social consequence. But, you know, I think AI is not so big and bad as, and I think the concern I have between regulation and, you know, I think we in this audience are critical of AI. I don't think I'm going to have generative AI drive my cars anytime soon because, you know, hallucination is like a polite word for screwing up. You know, I think that, but that doesn't mean I don't feel endless optimism for what it can do. And I do think, and I think my colleague Stuart, who's here a lot, I think, also doesn't think that. What he's worried about is people just turning the crank. And by the way, the Siemens guys talked about self-driving. You know, all the self-driving companies, and I know about Tesla because and the supply of my graduates go to work for Tesla. You know, they are being actually quite responsible. And people talk about, well, they run over a baby or a grandmother. You know, that's all. You know, people are not so sold, and that's this tension between reinforcement learning and safety. Safety is real, you know, and regrets are ensemble properties, whereas safety is the one sample function we all get to live. So, you know, but these are not insuperable. So I think Lighthill was wrong. I really do think that. You know, there was okay, sorry. My wife's we get long-winded as I get older, but in the Tony Blair government, there was a person called Sainsbury. You know, the Sainsbury of the chain of, he wrote, I thought, a much more balanced version to Lord Sainsbury to undo the damage of the, okay, sorry, stop. that was a technical question, right?
Very good.
Tamer.
Can't say no.
Hey, Tamer is one of the early heroes of this.
I have actually two questions. One is, you know, in transportation, there is this paradox, brass paradox,
Yeah.
where you build a bridge and that does not improve congestion. Actually, it brings an additional sort of levels of congestion. Does your tolling have any of these consequences that you play with the tolling and then the congestion goes up? That's the first question. The second...
Can I answer that, and I'll let you answer that?
Sure.
So the thing, for everybody in the audience, the thing in transportation called the Braze paradox, B-R-A-E-S-S, which is that when you add extra lanes, you may not help everybody's life. And actually, the reason you don't is because you leave Nash, you get, a big reason for the Nash equilibrium is because you don't have an overlay on top of that, of pricing. And part of introducing pricing, it sounds like a really rabid capitalist thing to say, the pricing really fixes the paradox. If it's a free good, it causes havoc. You've got to price it.
If you do it properly.
If you do it right, yeah.
Yes. The second question is, in all these problems, the number of players is very large.
Yeah.
Does mean field games have any role to play?
Okay, so I do think mean field games and non-atomic games have a huge role. And you're working on it. Asu Ozdaglar is working on it. John's former student at Cornell. Her name? Yeah, Parise. She's working on this. I do think, the modeling of populations and how many populations to model and then extract. And we had to do some of that in this willingness to pay. And this question of three population levels and the transportation guys. So I do think once you've done that, I do think these non-atomic games or population games and mean field games, I think they're going to be hugely useful. And I think learning the parameters, et cetera, will be quite interesting. And,
Thank you.
Yeah.
Thank you very much for your questions, and thank you, Shankar, for the nice talk.
Thank you.